Hey everyone, I'm Xudong, but feel free to call me Dongdong. I'm excited to walk you through our new dual series course. This course is split into two main parts. The first part is about porting the operating system, including migrating RISC and RTT to the movie dual. The second part dives into using peripherals like accessing camera display content, obtaining temperature and humidity sensor data while the dual, and even controlling a servo model while the dual. Alright, let's jump into Part 1, Lesson 1, RISC on the dual. This lesson consists of 3 sections: an introduction to the movie dual, an overview of RISC, and the quick porting process of RISC to dual. First, let's meet the dual. The dual is an ultra-compact RISC development board launched by RISC-V. It features 5 major modules. At the very top, we have Type-C interface, which is used for power supply and can also transfer data when connected to a computer. Right below the Type-C interface is camera interface, which allows for camera connectivity, and just beneath that is a chip, which is CV1800B. The CV1800B chip contains 2 cores, the B signal O6 core and small signal C core. The B core runs at a frequency of 1 GHz, while small core operates at 700 MHz. CV1800B is a high-performance chip with low power consumption, designed for various consumer IP cameras, smart home products, etc. It boasts integrated H.264 and H.265 video compression encoders and ISP, supporting a variety of graphic algorithms such as digital white dynamic range, 3D noise reduction, defogging, and lens distortion correction. Additionally, the chip includes proprietary intelligent reference designs for features like human detection, error detection, and motion detection. It comes with built-in DDR and full-set peripherals, as well as secure boot, secure update, and secure encryption functions. This provides a comprehensive range of security solutions from development and mass production to product application. The CV18 series comprises 2 branches, the CV18O series and the CV81 series, with similar chip in both. The outermost layer is our fifth module, which deals with peripheral connectivity. Details about the dual specifications, including its size, are on right side of PPT. The dual is incredibly compact, measuring just 21 mm by 51 mm and supports 64 MB of DDR memory. Regarding the outer metal contacts, we have an illustration that shows the button featuring a 100 megabit per second Ethernet port, along with 5 sets of serial port tools. In RISC, we primarily use UART-O, which also supports PWM. Let's delve into RISC. RISC is an operating system kernel designed and developed by Professor Wang Chen in 2021 for educational demonstrations. Its charm lies in its elegant and clever design. The entire kernel is made up of only 100 lines of effective code, primarily written in C with sprinkled assembly language. The code is not just concise and easy to read, but also straightforward to understand and maintain. RISC showcases a variety of core functionalities, including memory allocation management, primitive memory scheduling, simple software module exclusion, timers, both hardware and software timers, and it even works through whole system. Calls are made from user mode to machine mode. This lightweight operating system isn't just an excellent teaching tool, it's also a practical, expandable demonstration system that simplifies the design and implementation of fundamental operating system concepts. Before we get started, let's talk about preparation work. When you are porting, there are 3 tools we'll need. The first is a dual build root SDK, which gives us the initial image system for our movie dual. Next up is the RISC system we are porting over. And lastly, the toolbox. The goal of this project is to package the OS being compiled in RISC in the flip bin that can be read by the dual. Let's take a closer look at the dual build root. The dual build root is essentially our go-to for generating image that can be directly written onto our SD card. The README is super clear, telling us that we can use the build.sh script to compile all the necessary scripts. But since we are focusing on the movie dual, We can streamline the process by appending MuVideo to the build sh command to compile the image specifically for Duo. I've already completed compilation, which finished on this our timestamp. Now let's check out our current disk storage situation. We've got 2 disks. The first is in the built-in NVMe on our computer, and second is our SD card. Remember, when writing the image, we need to make sure to direct the DD of command to our SD card path. So let's get started with the writing process. To write the image, we use the DD command with offset to DV, SDA, and block size of 4 MB. While that's happening, let's revisit the dual build route. If your computer isn't up to snuff or you'd rather not compile, you can download and release the version. The latest is Duo 1.0.9. Compiled on February 28, 2024. You can download it directly and burn it into SD card. The advantage of compiling it yourself is that you can customize the compilation options. For instance, you can allocate all the RAM to the operating system instead of the camera algorithm, making the Duo a full 64 MB RAM device. However, if you don't want to set up the environment or your computer performance is lagging, it is recommended to use the latest official release. Then let's talk about RISC-V. RISC-V is the course previously updated by Professor Wang Chen on Bilibili. The latest content we need to modify is in Chapter 11 of the CodeOS, which is the newest chapter and includes all the content from previous chapters. We just need to modify this chapter to fully port RISC-V. Alright, our SD card is now written. Next, we'll insert SD card into the MuVideo. Then we connect it to our computer via serial port. And finally, we plug in the power for the Duo. When we boot up, the first thing we see is the invocation of OpenSBI, followed by the transition to the latest operating system. The serial port I'm connected to is UART0, and we can use the command uname to check our system information, including our current kernel version, which is 5.10.4. The entire system architecture is RISC-V. We can also observe that the blue LED light on the board is blinking, indicating that our board has booted up successfully and is in normal operating state. Now let's move on to the porting of RISC-V. I've already completed the porting, so we can just look at the commit for details. The porting process is divided into 2 parts. The first part is the architecture-based porting, where we need to port original RV32 architecture to RV64. This is because when Professor Wang Chen wrote RISC in 2021, it was based on our RV32 architecture, and now we need to port it in to match the entire system's architecture. The second part involves modifications based on the chip design, such as definitions of the serial port, interrupts, and timers, which are all based on the specific details of the chip. Let's start with the modifications from RV32 to RV64. The first step is to expand our registers, which were originally 32-bit in length, to 64-bit. So in the types file, we'll change the register width from unit 32 to unit 64. In the entries file, we have defined some macros. These macros originally set intervals at 4 bytes, which is 32 bits. Now we need to expand them to 64 bits. So we are increasing the intervals from 4 bytes to 8 bytes. This includes expanding the byte size for all content below. We'll also find that the original instruction used was SW, which can only operate on 32-bit data, and on 64-bit data, we need to use SD instead. Similarly, LW needs to be replaced with LD, and we'll need to make corresponding replacements in some of the function operations as well. Moving on to the memory S file, this is where our paging information is defined. When setting up paging, we can see that it originally used Word, which only allows for 32-bit memory space. We need to use dword to allocate double word memory space in our 64-bit operating system, so here we replace Word with dword. Then in the page C file, we define our page information, which needs to be switched from the original 32 bits to 64 bits. With this, our porting from RE32 to RE64 is complete. We can see that migration from 32-bit architecture to 64-bit architecture is quite straightforward. We just need to expand our registers from 32 bits to 64 bits and modify the previous 32-bit operations to instructions that can operate on 64-bit registers. The next step involves making some modifications based on our CPU design. In the platformer H file, we can see that my CPU is defined as 8. However, although the CV18OB has 2 cores, our ROS only runs on one of them, so we need to change my CPU to 1. Moving forward, we come to the UR section where URL's base address and interrupt number are defined. From PPT, which references the CV18OB chip manual, we know that URTO's base address is 0 plus 04144/40 and its interrupt number is 44. With this information, we can update the definitions for the UR, changing URO to 0 plus 0414/40 and set the interrupt number to 44. Then we adjust the UR execution logic for UART-REG. There's a left shift by 2, so we need to shift the register left by 2 bits. Next, we calculate the baud rate. Originally, the baud rate was calculated using 1.8432 MHz. But now we need to calculate it using 25 MHz. The chip manual provides a complete example on page 435, showing a baud rate calculation formula. It concludes that 256 times DLH plus DLL equals 25 MHz, which is our frequency divided by 16 plus 115,200, resulting in 13.5. So we get 256 times DLH plus DLL equals 13.5. Since DLH can only be 0, any integer greater than 0 will result in a number greater than 256 when multiplied by 256. DLH is set to 0. DLL equals 13.5, which will round to 14 as we define integers only. The hexadecimal representation of 14 is 0 plus 0e. Therefore, we assign DLL a value of 0 plus 0e. Continue on, we expand the number of bits for IR from unit 8 to unit 32. This completes the modifications for sending data through the UR for the dual. If we are receiving data through the UR, we are implemented a truncation during reception. Without truncation, the UR might remain in a continuous data receiving state, getting stuck there. Thus, we've added a truncation, and with that, our modifications to the UR are complete. Let's return to platformer.h. After completing the UR modifications, we move on to the interrupt section. Looking at the PPT, we see the PLC interrupt registers. The base address for PLC is also found in the chip manual. However, we obturate the device tree information for CV180, which clearly states the base address for PLC as 0 plus 7 followed by 70. We update the PLC base to this value. Continue on, we know that CV18OB contains 2 C906 cores, so the internal implementation of interrupts is actually carried out by the C906. Consulting the C906 chip manual, we obtain a table that includes the interrupt pending register, machine mode interrupt enable register, interrupt threshold register, and machine mode interrupt claim and complete register. All these are offset based on PLIC. For example, the interrupt pending register has an offset of 0 plus 130 from PLIC for interrupts 1 to 31. For interrupts 32 to 63, the offset is 4 times greater compared to the pending register for interrupts 1 to 31. Therefore, we define the interrupt pending register as the PLIC base address plus 0 plus 130 plus the interrupt number divided by 32. For instance, if the interrupt number is 30, its pending register is POS address plus 0 plus 130. For interrupt number 44, the address will be PLC plus 0 plus 130 plus 44 divided by 32 times 4, resulting in PLC base plus 0 plus 1004, which matches our definition. The machine mode interrupt enable register's definition is similar to the pending register. Its offset from PLC is 0 plus 230, which an offset of 4 for every 32 interrupts. Thus, the machine mode interrupt enable register is the PLC base address plus an offset of 0 plus 230 with an additional offset of 4 for every 32 interrupts. The machine mode interrupt threshold register has only one entry with an offset of 0 plus 2 followed by 40 from PLC. The machine mode interrupt claim and complete register has offset of 0 plus 2004 from PLC. With these definitions, we can modify our code accordingly. The interrupt pending register remains unchanged with an offset of 0 plus 130. The machine mode interrupt enable register previously modified based on hard is not actually related to hard, so it directly offset it by 0 plus 2000, adding the ID divided by 32 times 4. This aligns with the definitions we saw in the table. For the machine mode interrupt claim and complete register, we remove the hard content and modify it according to the table's definition. This concludes our modifications to the PLIC interrupt registers. In the implementation phase, we first remove content related to multiple hard cores because we only have a single core type. Therefore, the first step was to eliminate all content related to hard. Next, we observed some modifications in the interrupt enable register. Looking at PPT, the C906 chip manual explains how the interrupt enable register stores information. For an interrupt with IDN, the interrupt enable register information is stored in PLIC-IX, where X equals N divided by 32. This PLIC-IX is what we defined earlier in the machine mode interrupt enable register. This is a previously defined X. On the X register, the interrupt, i.e. Y, is determined by Y equals N modulo 32, where modulo denotes the modulo operation. For IDO, the corresponding I is permanently set to 0. To illustrate, let's take the URO interrupt as an example. URO is located at PLIC-IX, where X equals N divided by 32. Here, X is taken as 1, and Y on the IEY register equals N modulo 32. For interrupt number 44, 44 modulo 32 equals 12, so Y is 12. The 12th bit position on PLIC-IX is what we were interested in. The storage method for this register can be visualized as follows. The 0th bit is the first position set to 0, so the 12th bit can be understood as counting 12 positions to the right from 0. This means that if you want to set 12th position to 1, we only need to left shift 1 by 12 bits. This gives us the following expression. For instance, if you want to store the interrupt for URO, it is stored in PLIC-IX, whereas it's a result of URO modulo 32 and Y is URO modulo 32. Then we left shift 1 by 1 bits. These modifications pertain to the interrupt enable register. With this, our modifications to PLC are all complete, meaning all changes related to the interruption section are finished. Continuing our review, we move on to the timer section. The timer's address and clock frequency are obtained from the chip's device tree. The base address is 0 plus 74 followed by 60, and the clock frequency is 25 MHz. We'll start by updating the base address to 0 plus 74 followed by 60 and the clock frequency to 25 MHz. Looking further, we refer to the C906 chip manual for the definition of CLINT. We focus on two parts: the machine mode software interrupt configuration register, which is our MSIP register, and its address is the same as our base address, 0 plus C74 followed by 60. The key part to examine is the machine mode system timer compare value register. It is divided into high 32 bits and low 32 bits for storage, which is slightly different from our understanding of a 64-bit machine mode system timer that stores directly. Therefore, we need to modify according to this definition. For instance, the low 32 bits of the machine mode system timer compare value register are offset by 0 plus 430 from the MSIP, and the high 32 bits are offset by 0 plus 4004 from the MSIP. This gives us the definitions for the low and high 32 bits of the machine mode system timer compare value register, which will update accordingly. After these modifications, we notice that we are missing a cleaned M-time, the M-time register, which is actually used to obtain the current clock cycle. Since we couldn't find the M-time register in the C906, we use the R-time function in RISC-V.H to get current clock cycle. The R-time function in RISC-V.H returns the machine mode clock cycle, which is consistent with the M-time content we read earlier. Thus, we use R-time to obtain the current clock cycle, replacing the old RISC-V.H with one that supports the R-time function. After replacement, we found that unit 64 is used in RISC-V.H, but we haven't defined it. We can simply add it to types.h as a long integer type unit 64. Continuing with our implementation of the timer, we first removed all content related to hard, as we are working with a single core setup. In the original code, the machine mode timer compare register was directly set to the current clock cycle plus one offset. However, we are now dealing with high and low bits, so we defined a unit 64 type variable named time to record the current clock cycle plus an offset. We then split this 64-bit type variable and store it into the low and high 32-bit machine mode compare value registers. For the low 32 bits, we simply use a bitwise AND with 32 ones to extract the low bits and store them directly. For the high bits, we shift the high bits right by 32 positions, placing the high content in the original low bit position, and then perform a bitwise AND with 32 ones. This completes our modifications to the machine mode timer compare register. The remaining part involves continuing to remove content related to hard and multi-core support. Additionally, when obtaining the return value from interrupts in the original 32-bit program, we only need to compare with a 32-bit 0 plus 8 followed by 70, but now as we are working with the 64-bit operating system, we need to extend this by adding 8 zeros, making it a 64-bit number for comparison to get correct return value. Otherwise, we cannot obtain the interrupt return value through this intersection method. So far, our modifications are essentially complete. The remaining parts are just some changes related to multi-core and obtaining the core ID. We remove hard since we only have one core, Additionally, in the compilation process, we can see OSLD that the memory was originally defined as 128 MB, but in fact, our new video only has 64 MB, so we need to change the memory definition to 64 MB. This concludes all our modifications. One difference in common MK is that C flags were still set for compiling with RV32, which we need to replace with RV64. The only significant change is that we've added a new parameter, MC model equals Medani, which means our model is a medium model. During compilation, it will choose between a small or large model based on our dynamic address, avoiding errors due to memory address space limitations. Our tests show that without this addition, the overall compilation cannot proceed. Next, I'll compile the code. In this code, we simply run make. This code has already been modified by me, so we can directly make and see that OSB is generated. Now let's look at the contents of the SD card in our new video. I insert the new video's SD card back into the card reader to check. Then we'll use the mount command to mount. We can see that our mount actually contains two parts, boot SD and FIFBin. Boot SD is the real-time operating system running on small core, and FIFBin is the Linux operating system running on the big core. We need to run our RIOS on the big core, which means encapsulating OSB into FIFBin. For this, we use another tool, the dual toolbox we talked about earlier. Its main purpose is to package our own RIOS into FIFBin. The README specifies that if we need to generate a standalone RTOS FIFBin, we must first generate the SBI within the bootloader directory, then proceed to do RIOS to replace the existing RTOS bin with our OSBin, and finally compile a new OSBin. Afterward, we copy both OSBin and SBI bin to the FIB directory and use make fsbuild build to create a new FIFBin. Following this process in the toolbox, we go to the debug loader directory, then to SBI and use build sh to generate SBI, which is located in the fdub-bin directory. This is a newly generated SBI. Then we return to the bootloader and go to do RIOS. When the first step is to replace our RIOS OSBin with RTOS bin, we can do this directly using the cp command to replace the original RTOS bin with the OS bin from the CodeOS 11 Cisco directory. Then we compile to produce the new OS bin, which is now ready. Next, we go to the FIB directory, copy the SBI bin from the bootloader fdub bin to the FIB directory, and then copy the new OS bin from the RIOS to the FIB directory. To generate the FIB, we need to add environment variables because we will be using our own compiler, the GCC in the host tools. These tools are downloaded when we first clone the repository and run the init program. We add these environment variables and then execute make fsbuild build to create a new FIFBin. Once FIFBin is generated in the build directory, we write it to the SD card. Since we've mounted SD card to MNT, we can replace the existing file with sudo cp FIFBin mnt FIFBin. Then we unmount MNT. Now we can insert the SD card back into the new video and then connect the serial port to demonstrate the running state of RIOS. I've already connected the serial port and started the system. After powering on, we can see it's printing, but the output only has line feeds without carriage returns. Adding carriage returns would make each line start at the beginning, which would look better as it is. The output is not very visually appealing. In the serial port tool, we have made a modification. There is a parameter called mmap, which is used to format our input and output. For our PC, this formatting involves replacing line feeds with carriage returns followed by line feeds. This way, every line feed is replaced and it will display at the beginning of the line. Now let's run it again. We can see that the display content is now well organized, and let's outline our operating steps. First, we printed hello RISC, which is the first line printed in kernel C. Then we printed our paging information. We can see that test 0 has started to be created. We found that we are running in user mode, encounter interrupt error, and then switch to machine mode and continue running, which is implementation of our system code. According to the timer, different ticks are printed. Let's try the serial port interrupt. We pressed 1 and 2. After pressing 1, it shows that a serial port interrupt occurred and then outputs our current content. This entire operation logic of RISC. With this, our porting of RISC to the movie video is complete. Thank you very much for watching, and if you have time, you can try it out.